Okay, so we're going to quickly talk about magnetic fields. So all magnets have two poles. They have a north, oops, gotta do this, a north and a south pole. This pair makes magnets dipolar. Okay, the attraction and repulsion occurs. It actually uses electric fields. So what we learned in the last video or Zoom call about electric fields, how it goes out of the positive into the negative, and it's using electrons and protons. Magnets are literally using the exact same thing. So things that are really, really good magnets, elements that are found in groups 8, 9, and 10 are usually really good magnets, and we call them ferromagnetic. So a good example would be iron, okay, but also nickel and cobalt are three examples of things that are ferromagnets. So ferromagnets are good magnets. These are things that naturally become magnetic super easily. They make good magnets because they're made up of tiny magnetic domains, and they are all aligned together. So in this picture, you can kind of see what I'm talking about. I put two T's there, sorry. These little tiny magnets that make up the substance, when they're all aligned in the right orientation, that makes something magnetic. So everything has the ability to become magnetic if it unmagnetizes. Like old magnets might not be magnetic anymore. If you touch it to a really, really strong magnet, it will actually align those little small magnetic domains and line them up again. So this is showing two really strong magnets, and they're attracted together so strongly that it's actually cracking a pencil and squishing it. So these strong little magnetic domains are basically just places in, or atoms, I guess, in the material that have kind of a positive side and a negative side to it. So if all of the positive sides and the negative sides kind of line up, which correspond to our north and south poles in a magnet, then that's where things become magnetic. So magnetic fields, when we're talking about that, are operated by or generated by two things. So either the movement of electrons around a nucleus, and the spinning electrons around its axis. I won't write that down because we get it, electrons. Also the electric current, passing through a coil. So just a regular magnet, when you see the magnet, the movement of the electrons in those atoms is what is actually causing the magnet to be magnetic. But you can also make a magnet out of a coil of wire and sending electricity through it. So the electrons moving through that coil of wire also create a magnetic field. They're called electromagnets. When we're looking at magnetic field strength, we're not actually using any sort of formula here. So we're not calculating magnetic field. All you guys have to understand is that as the magnets get farther away, the magnetic strength is going to decrease. Sorry, I forgot the R. I was like, that looks weird. And increases with the strength of the magnet. So if the magnet is a stronger magnet, then the magnetic field is going to be stronger. Now, when I was in university, I used to work at a science camp at U of A, and we had a couple of strong, really, really strong magnets that we used for a demo. And when we put it away in the summer, I got stuck against the filing cabinet. And the next summer, we literally couldn't remove the demo from the filing cabinet because there's such strong magnets. We physically could not remove it from the filing cabinet, which was metal. So we're just going to look at, when we're talking about in science study magnetic fields, we just have to know like the direction of the magnetic field. So basically being able to draw a magnetic field diagram. So we use to determine what the magnetic field is, we use a north test body, and it always goes out of the north into the south. Okay, just like in an electric field, it goes out of the positive into the negative. So it would go out of the north into the south. It would look like this. This side would be the south pole. This side would be the north pole of this magnet. So we have to draw the field lines as well. So, and it would also go like this, out of the north into the south. And we would have lines coming in like that, and out of the north into the south. So that's kind of how my diagram would look. So as long as you can remember out of the north into the south, that will make it a lot easier to draw any of the field lines. So if you have magnetic field lines with magnets that are the same poles, okay, we know that opposites attract and the same like charges will repel each other. So because it goes out of the north into the south, these field lines would look like this. And that's why they're repelling each other. They're not going to be connected to each other. Same with our south pole. It would just be a little bit different because it would be going like this and like this. But we wouldn't have any connection between the two south poles. So that's why they repel each other. And that's what our field lines actually look like. Okay, so magnetic field lines in an electromagnet using the coil of wire. If the coil is the direction, if given a coil, the direction of the field lines is similar to the one on the left. So it's going out of the north into the south. But that's also looking where we have current going into the thing and the current going out. So that's how we actually end up getting our field lines. So if the current's going in, that becomes our south pole because the electrons are going in into the south, and then out of the north, it's going out. So that's how we determine our field lines. Let's just fill in our blanks. So the coil without a field labeled, where the current goes in is the south pole. So that's good, easy to remember because it's just sticking with the same rule that we were just doing. Now, Earth actually has a magnetic field. That's why a compass works. So compasses always point north because of our magnetic field. The reason that we have a magnetic field is because deep down in the core of Earth, there is an iron core. So it's the movement of electrons inside of this iron core. So remember that movement of electrons generates an electric field, which is a current, and we need a current to create a magnetic field. Okay, our compass needles are basically our north test body. They always point north, which we say is geographical north, but that actually means that if our geographical north pole is having the north test body point to it, that means that it's actually the magnetic south pole. Because remember that it goes out of the north into the south, so that north test body would be going towards the south pole because opposites attract. North and south pole attract. So our compass always points up, and that's because the magnetic south pole is actually on the top, at the technical geographical North Pole, which is super random. This is really interesting. Some organisms, like birds, for example, and salmon, they have sensors inside their body. Like we have like sensory cells that take in light and sound and use that in our brain to figure out kind of what's happening around us. Birds and salmon and other organisms have sensory cells that actually sense the magnetic field, and that's how they know, like in the fall, when birds fly back north or fly south, and then in the summertime they fly back north. They know what direction is what because of these magnetic sensory cells, which is super, super cool. I wish we had that. Then everyone would have a really good sense of direction. So now that we have all of the magnetic field information done, I'm just going to quickly go through this with you as a review from all of the things that we've learned so far in the physics unit. So if you have a gravitational field, this is created by any large mass. Any large mass creates gravity. We use the formula little g equals big G times m divided by r squared. And our vector diagram would be usually a planet, and we have gravity pushing towards the center of the planet, okay, keeping everything on that planet. And then our graph that we have, if we went that gravity versus our distance, it would decrease as we got farther away. Okay, for electric fields, this is moving electrons create an electric field. And our formula is our capital E with absolute value lines on the other outside of it. And we go KQ over R squared. It's our formula. And for this, we have, if we have a positive and a negative, it goes out of the positive into the negative. So our field lines would look like this, out of the positive and into the negative. For this, our electric field, as we get farther away, the field strength decreases again. And moving on to magnetic field, a magnetic field is created by an electric field. We don't have a formula that we use for a magnetic field. Okay, we just need to know how to draw our actual field diagram. So if this is north and this is south, remember it goes out of the north into the south. And we would also have it looking like this. So it looks something like that. And same with all of the other ones. As our distance changes, our magnetic field is going to decrease. So hopefully that is helpful for a summary of everything that we've been doing for the last couple of days. If you have any questions, please let me know. I apologize for the technology issues that I was having today. So hopefully this works. Talk to you later. Bye.